Hello everyone, welcome to this KANPUR-NPTEL online course on space environments and its effects on orbital spacecrafts. So, in this module we are discussing the effects of neutral space environment on the function of the spacecrafts. So, we have seen the different types of effects, namely we have seen how the atomic oxygen which are dominated the low earth orbit of the satellites, how it impacts the spacecraft materials in terms of the erosion than the spacecraft glow. Then we have seen in the that we discussed in the last class, that is the effect of atmospheric drag. So, though we in the beginning we discussed that this spacecraft environment is vacuum like, but still there is the whatever the residual atmosphere is available there, the very low density atmosphere that is sufficient to create the drag on the spacecraft, which give rise to the changes in the various, that is the orbital parameters of the spacecraft. So, orbital parameters means it is the altitude and the orbit, and we derived this equation, that is how the altitude of the orbit changes with respect to time. So, the rate of change of the altitude of the spacecraft with time, as well as the rate of change of the orbital period with the time, that we have derived the formula, and using those things we also derived a formula that is a very ideal formula for the life of the spacecraft. So, that is in terms of the scale height as well as the rate of change of the orbital altitude of the spacecraft. So, today we will start, that is our topic will be different. Here we will consider the particulate environments, and the particulate environment they consist of the micrometeoroid and the orbital debris. So, we will just see what are those things and how they affect. So, basically here the effect is it is called the hypervelocity impacts. So, we will see what is the hypervelocity impacts and how this particulate environment, this is very detrimental to the health of the spacecraft. So, now the question is what is hypervelocity impact? So, hypervelocity means when the velocity is more than the velocity of the sound wave. So, sometimes it is when it is 5 times more, that velocity is called the hypervelocity. So, hypervelocity is it refers to the range from a few kilometers per second to some tens, it can be several tens of kilometers per second. So, if that is the velocities of the particles, and when this type of particles they impact the spacecraft, then we call it the hypervelocity impact. So, this is very relevant to the field of the space and human made assets, where the hypervelocity impacts are caused by meteoroid, then it can be micrometeoroid, then the space debris. So, what is a meteoroid? Meteoroid is a small piece of celestial material which orbits the sun, and it is generated, can be either from the comet or the asteroid. So, asteroid means when there is a collision between the asteroids, it can create the meteoroid shower. And the micrometeoroid, this is a very small, it is in terms of the microns. So, that is why it is called the micrometeoroid, with mass typically less than a gram. So, that is called the micrometeoroid. And what are the orbital debris? So, orbital debris, these are the main objects in orbit and which are not carrying out any useful functions, like the spacecrafts or the space shuttle or the space station. So, these are not performing any function or any useful functions. What are the examples? The examples are like the rockets. So, they are the upper stages of rocket which are used to inject the spacecraft into orbit. So, that after the injection, so this may remain in the orbit and without doing any useful function. So, this will act like the the debris. The other, it can be the different types of the clamps which are used in these rocket stages. Then the D-spin cables. So, these are also used to control the spin of the spacecraft bodies just when it is released from the, or it is separated from the launcher. Then there can be the metallic fragments. This can be from the different the separating the mechanisms, or it can be the parts of the rockets, then the paints, then the rocket exhausts, or the remnants of the launch vehicle. Then it can be the, sometimes the spacecraft may collide with another spacecraft, there can be the explosions. So, all these things when created, these are called the orbital debris. So, these are the man-made the pollution which is created in the orbit. So, all these particles, they are moving with a very high velocity, this is the hypervelocity. So, this hypervelocity when there is the impact by this hypervelocity objects, so that can result from the minor component degradation. We will see what is minor component degradation to the complete destruction of the spacecraft. So, where from this destructive energy come from? So, this is the consequence of the high impact velocities, which can reach something like 15 kilometer per second for the space debris, and it can be more than 70 kilometer per second for meteoroids. So, basically the very whenever the velocity is very high, so its kinetic velocity will be very high, kinetic energy will be very high, and that kinetic energy will give rise to all this destructive impacts. So, now we will see what are the effects of this high velocity impacts on human assets. Human assets means, as I said already, whatever the spacecrafts, or it can be space shuttle, or it can be a space station. So, all whatever the the space objects or the spacecrafts and the other the assets are there in the orbit, it is exposed to certain flux of impacting either the meteoroid or the space debris particles. So, these impacts occur at typical velocities, as I already said, it can be from a few to tens of kilometer per second. So, now depending on the size, so if it is a sub-micron, sub-micron means it is less than 1 micron, sub-micron I mean to say that it is less than 10 to the minus 6 meter, means 1 micron, or micron size particles can lead to degradation of sensitive spacecraft surfaces. It can be the glasses of the camera, or that is the mirrors, or the it can be the optical as I already said, the optical sensors, or the thermal control surfaces. So, somewhat larger particles with the diameter in the size range of tens to 100 of microns. So, 100 micron means 0.1 millimeter. So, these particles, when the size is having this range, they can penetrate the outer surface coatings, the foils, as well as the solar cells. Now, when the impacting particles are of millimeter size, so that time it can penetrate the exposed fuel tanks. So, the fuel tanks which are used in the spacecraft, that is for the orbit control or the attitude control. So, those it can penetrate the fuel tanks, also it can seriously damage certain other equipments. When the impactors of it is of size as of centimeter or larger, it will typically lead to complete destruction of the impacted spacecraft part. So, in addition to this mechanical effects, every hypervelocity impact creates plasma. So, this discussion will not do it here right now, we will do it when we discuss the plasma environment. So, there we will discuss this how the plasma is created, but because of the impact and because of the high energy, this impact of the impinging particles, or because of this energy transfer, some of those the particles from the impact it can get charged. So, that is why the term is coming that is the plasma. So what will this they do this type of, the plasma particle means whenever a plasma particles, it is the moving plasma. So, means moving charged particles. So, moving charged particles will give rise to the current and the associated field, and which will create the interferences. So, that is why these are called the electromagnetic interferences or EMI, and that can affect the spacecraft system and payloads. We will discuss in more when we this topic, that is the plasma, that is called the induced plasma by the spacecraft itself. So, each of these categories, so we discussed the different categories starting from the micron size to centimeter size, but so this requires different mitigation strategies, we will see that, and the shielding design to ensure the safety of the space assets. So, there is some shielding, and there are the other way also that to mitigate this problem. We will discuss this one by one. When the particle size is above it is 2 to 4 centimeter in diameter, it is impractical to provide in the shielding protection. So, there the solution is to do the avoidance. So, there are the collision avoidance mechanism is there. When the particle size is bigger, when it is few centimeter, it can be observed by the sensor systems, and then accordingly the spacecraft can be maneuvered, so that those collisions are avoided. Okay. Now, the effects by hypervelocity impact. So, the effects of the hypervelocity impacts are a function of the projectile. Projectile means the particles, the moving particles, and the target material. Target material means it is this is the spacecraft surfaces. And what is the impact velocity? Impact velocity of those hypervelocity particles. What is the incident angle? At what angle it is striking the surface? What is the mass and the shape of the projectile? So, it depends on so many parameters. What will be how it will affect the spacecraft surface. So, we will see that with the decreasing target thickness, the effects will range from creating the crater or it is also called the cratering, via internal cracks to spell. Spell means detaching some surfaces or some of this coating. So, this is called the spell detachment. Finally, it can even create a clear holes, perforations on the targeted surface. Now, how this thing is this assessment and the prediction of hypervelocity impact of particles with spacecraft, we will see what is the way these things are done. So, there are three primary means to assess and predict what is the potential damage to spacecraft from the impact of hypervelocity particles. So, you can do the testing, that environment can be simulated, and so you can do a hypervelocity impact testing on the ground itself, on the earth itself, on the laboratory environment. There can be analytical analysis and digital simulations. So, those particle sizes, the velocity and their impact, these things can be simulated digitally. There can be in situ observations. So, there are various types of that is the return, like those the capsule which are used to take the astronauts to these space stations or bring them from the space stations or the space shuttles. Okay. And there was there were some there was a mission, it is called LDEF. LDEF, long exposure long duration exposure facility. So, this was a mission, and it is just a cylindrical the structure where the materials, the other substances were put in some panels, in a cylindrical panel, and it was there in the Earth's orbit for around some 5 years, and finally, it was brought back by attaching to a space shuttle, and this also gives a lot of the inputs, how this what is the spacecraft environment, and what is the environment that spacecraft was exposed, and what are the effects. So, these are the three ways you can do it. So, the assessment of the potential damage of the hypervelocity impacts is accomplished primarily through experimental testing. So, you get the data from the experimentation, then you do the analytical or the digital course, and whatever the limited the on or in orbit data are available. So, this can be used to validate or the confirmation of the analysis, those can be used. So, for the damage and the risk assessment, the penetrability of a projectile into a structure is needed. So, some modeling is needed. So, we will just now see how we do that thing. So, there are some the various types of configuration of the shield is used. So, it can be a single surface, single layer shield or multi-layer shield. So, we will consider here one shield, it is called the Whipple shield configuration. So, this is a classic the Micrometeoroid protective structure which was proposed by Fred Whipple, and that is why it is called the Whipple shield, and it is made of two thin aluminum alloy plates with a certain standoff distance. You can see it here. So, these are the two plates. So, this is the front plate and this is the rear plate, and this is the projectile, that is the impacting object, and then it is striking here. So, it can penetrate, and we will see it what happens and what can be the different possibilities when a hypervelocity particle is impacted is impacting this the front surface, and how it what happens after that. So, the primary function of the front plate, so this plate front plate is, or it is also called the bumper of the Whipple configuration, is to break the hypervelocity projectile into a debris cloud of structure consisting of large number of fine fragments. We will see how this is advantageous, that is using a this is the bumper. So, since the impact, this energy of the initial projectile distributes into lot of smaller fragments, the impact damage on the rear plate, means this is the useful, the rear plate also it is the shell of this spacecraft or it can be a space suit. It can be elevated, means it can be decreased accordingly. So, evidently the bumper plate plays a very important role in the protection of the performance of the micrometeoroid shield configuration. So, the protection concepts for the spacecraft from meteoroid and debris particles rely primarily on positioning the metallic shields or the bumps in front of the critical surfaces by a variety of configurations. I showed you only the two surfaces, it can be the multiple layers. So, this is the simplest one which is suggested by the Whipple. So, you see there is the projectile, means this is the hypervelocity particle, and this is the bumper or the front shield, and this is the rear wall which is the skull of the spacecraft, and this is the standoff distance. So, this is before the pre-impact. So, you see what is happening after the impact. So, when it is impacting, so this is becoming a number of the segments, and it is becoming something like a debris cloud, and you see this is not impacted by, in this configuration it is so that the rear wall is not impacted by that, it has been whatever has happened, it is around the front one. But so it is the post impact. So, this is one case. Other case can be if the energy and the mass and its velocity, all these things in such a way, so that even it is able to that is impact the rear surface, then this type of things may happen. Some craters or holes may be generated, it may get fractured, and there can be some detachment of some of the materials which is called the spall. It can be some protective layer or some coatings. So, the purpose of this Whipple shield is to fracture the hypervelocity particle into a cloud of smaller particles, whatever is shown here, consisting of the original projectile and the shield material with some of the materials, possibly it can be liquefied or it can be vaporized. So, because of that impact, whatever this impact and because of that compression, or because of the the whatever the material, there will be two types of the shock generated. So, because of this interaction, this it can be even the liquefied, or it also can be the vaporized. The effectiveness of this approach depends on the ability of the shield to redistribute the momentum of the material clouds of particles over a larger area that would otherwise impact without the shield. So, suppose if this shield would not have been there, this one. So, this is the actual the skull of the spacecraft. So, this would have been the damaged. So, this is the way the shielding this type of the Whipple shielding works, and this the Whipple shield has generally the mass advantage over single wall structure, because if I am to use a single wall LF, then the thickness should be more. So, thickness means the more mass. So, for the impacts where the projectiles mass per unit area is much larger than the shields, and its impact energy is much greater than that needed to penetrate the target, that is the energy transfer from the impact is not high enough to damage the projectile. The impactor can create a cookie cutter. We will see what is the cookie cutter. For it is for the thin shield it can happen. So, what happens? It punches out a crater roughly proportional to its cross section of the impactor in passing through the shield. In this case, the effects of the shield on the impactor are primarily a momentum reduction proportional to the mass of the shield material and the velocity of the projectile. So, when the hypervelocity particle strikes an object, a shock propagates in both the media. So, one is because of the material itself, it will try to what is because of the density and the material properties, it will try to. So, it is something it comes from the Newton's third law of motion. So, there is the shock waves. So, these two shocks are controlling the factors of the interaction. So, you can see this one, we will see what is this. So, what is the condition here? Here the shield is thin relative to the diameter of the particle. So, this is the diameter of the particle is d, the diameter of the particle is d, and T s is the shield thickness. So, this is the shield thickness, this is T s. So, if this is the case, what it will happen? In this case, the shock that propagates into the shield can reflect from the rear of the shield. So, this is the shock because of that impact of the particle and overtake the compressive wave. So, it is more than whatever the compressive wave is created by the material itself, the target material wave in the impacting particle. So, this disrupts the compression wave, so that the particle does not have time to get very hot. So, it can as it is go out, consequently the shield breaks into solid fragments or particle cuts into shape. So, that way is calling the cookie cutter. So, suppose cookie cutter means you have to cut something in some shape. So, here it is cutting in the shape of the impacting particle. Okay. Now, let us see the case when the thickness of the shield to the diameter of the impact. So, that ratio increases. So, it can reach a value where the reflected shock just overtakes the compression wave in the particle as it reaches the end of the particle. So, here this is the case shown here, that is when the thickness T s and so T s by d is this range is between 1 to 5. Okay. So, in that case what happens? By this time, depending on the peak shock pressure generated at the instant of impact, the particle will be heated to its melting or vaporization point. Okay. So, because now this thickness is more, so whatever the shock wave is provided by the impacting that is the target. So, what happens? Because of that that is the impact, so much heat is generated. So, there is the possibility that this impacting particle, that is the projectile as well as the material, both can melted or vaporized. So, what will happen because of that? So, it will give you the radial velocity. So, the particle will have the radial velocity, so that it can come out through this, this is the direction of the particles can come from the rear side. And what does it mean? That because of this, the shield is destroyed, and when the Ts by d continues to increase, means when it is very large as compared to 1, the reflected shock does not have time to overtake the compression wave with the particle. Okay. So, what happens? This impactive particle thus melts or vaporizes and moves cohesively into the shield. So, now this impacting particle as well as the target material, they move cohesively to the shield material. From the shield, it may be thrown from the back of the shield. So, this happens, this is called the spall, that already we spall of the shield. And if the shield has a low melting point, so then the spalled material is likely to be in melted state. Okay. Now, we will see this is the cases where the projectile does not penetrate the shield and the velocity is so high that it can be destroyed. The crater created should be proportional to the energy of the impact. So, whether it is the actual crater size and the shape both are dependent on many different physical parameters. The crude proportionality of the mass removed from the crater to either the momentum or the energy of the projectiles. These are the the starting assumptions for the mathematical models developed. We will just show you two mathematical models. So, one is the that is the model given by the Swift. So, we will just see what is that model. So, this model is given by this, where dm here. So, dc is the it is the crater diameter. So, what is the crater created by the impacting particle? dm is the projectile diameter, that is the impacting particle diameter. The rho m is the density of the projectile and bm is the velocity of the impact, and hf is the heat of fusion. So, because of the given particle may also vaporize or not melt smoothly. So, the general relation between dc and dm, this is it is written like this. So, this is if you calculate from here dc by dm and you put hf is equal to hf E0 is equal to hf by 2, you will get this equation. And just for an example, for the low density particle striking aluminum, so E0 is given by 10 to the power 9 joule per meter cube. So, we will just tell you the another formula which is also used, which is widespread use, that is called the KANPUR-NPTEL. So, this it is based on again the empirical fit to the data, and it gives. So, dc and dm, they are related by this. Again here this nomenclature for rho m and bm, dc, dm are the same what we discussed in the last slide. So, this is is the same, the dc is the diameter of the crater in centimeters, dm is the diameter of the projectile in centimeters, rho m is the density of the projectile in grams per cube centimeter, and bm is the velocity of the impact in kilometers per second, and c is a constant, that is the characteristic of the target material and its temperature. So, this these are just two examples I have given. This is a Swift and the KANPUR-NPTEL formulas. There are many other these types of the models are available, and the distribution of the particles at small sizes. So, what is the particle the size and what will be the crater size. So, there is some the distribution or the catalog is made. So, that is based on determined by measuring the crater size and the distribution on the samples of surfaces from return spacecraft. And then the scatter size is related to the mass of the particle diameter if given the density by the equations such as those which we have just said, these two methods. So, with this I will conclude it here, and in the next session we will discuss the how to manage the debris, and it will be similar type of the impact will be similar, but how the debris are managed, how it is captured and controlled, this I will be discussing in the next class. Okay. Thank you very much.